Ladies and gentlemen, it's my great honor to participate this conference and make a speech. My name is Zhang Liyan, the author of the paper A Novel Spatial Modulation Based on Cosine Function Pattern. Next, I will make a brief speech about this paper. The contents of my speech are divided into 5 parts. First, let me make an introduction about this paper. Spatial modulation is a type of massive MIMO technology which utilizes the index of transmit antenna to carry some information bits. It has many advantages such as simple transmitter structure, low power consumption, and few activated RF chains. Thus, spatial modulation gradually becomes one of the technologies that attracts much attention in massive MIMO area. According to the number of activated antennas, spatial modulation is classified into traditional spatial modulation and general spatial modulation, which activates only one antenna and more antennas respectively. Recently, a novel spatial modulation called ABPM appears, which uses the index of antenna beam pattern to carry some information bits. When the receivers are located at the cross points of all beam patterns, ABPM is better than traditional spatial modulation in terms of bit error rate. However, the probability that receivers located at the position above is low. In ABPM, there are a lot of available patterns to antenna array. If one receiver lies in the non-intersection area among different patterns, it cannot receive the electromagnetic wave from certain patterns, which results in some not recognized patterns in this receiver. Thus, ABPM cannot be widely used in application. To solve this intrinsic problem of ABPM, this paper proposes a new method of beam pattern modulation based on cosine function pattern. The scheme uses the Woodward-Lawson algorithm to calculate the weighted vector and is more suitable for mobile communication scenarios. The results of theory, analysis, and simulation show that MCBPM is better than traditional spatial modulation in terms of bit error rate and transmission rate. Next, let me introduce the model of ABPM including transmitter, channel, and the receiver. At the transmitter, the input bit vector B includes k bits. We convert k bits into 2 parts by serial to parallel conversion. The first m bits are divided into the first part, which are used to select a weighted vector W of transmit antenna by some mapping relation. The next k minus m bits are divided into the second part, which are mapped into many points of constellation graph according to the modulation type. The constellation point collection can be expressed as S. Then, multiplying the selected weighted vector W by the selected constellation point collection S, we can obtain the transmission vector X. The transmission vector will be transmitted to wireless channel H, whose arbitrary element follows the independent identically distributed circular symmetry complex Gaussian distribution. At the receiver, the received vector Y can be expressed as Hx plus V. We use the maximum likelihood algorithm to detect the transmitted k bits from Y. In order to understand the principle of ABPM, we take a 2x2 MIMO system as an example. The array response vectors and the two beam patterns are given out. Obviously, there is large difference between two beam patterns. The gain of beam pattern 1 at 120 degree is 1, and the gain at 60 degree is 0. The gain of beam pattern 2 is just the reverse. If the receiver can discriminate them, it will recover a bit information correctly. However, if the receiver locates at the right point in the figure, it cannot receive the signal carried by beam pattern 2. This is an intrinsic weak point of ABPM. In this paper, our proposed scheme can solve this problem efficiently. Let's look at part 3, our proposed scheme, MCBPM. The process of MCBPM is listed as follows. Considering one cell in cellular network, where a base station is located in the center of circular area and some user equipment are uniformly located near the base station. We divide the circle into n sectors equally and allocate different frequencies to different sectors. Thus, there are no interference among different sectors. The base station has many antenna arrays. Each of them is allocated to one sector. The desired beam pattern is described by the following cosine function. Next, we will design the weighted vectors corresponding to the cosine beam patterns. Here, we introduce Woodward-Lawson algorithm to calculate the weighted vectors from a desired cosine beam pattern. We can obtain the kth element of the weighted vector W according to the following steps. First, substituting the number of transmit antennas into equation 8 and calculating the sampling point θm. Calculating the discrete pattern value according to the desired beam patterns and sampling point θm. Next, utilizing equation 7 to synthesize the accurate pattern F. Finally, calculating the weighted vector W according to the equation 10. And now we have derived the weighted vector W of general array pattern. According to the uniform linear array response vector V and weighted vector W, we can obtain the final antenna beam pattern created by Woodward-Lawson algorithm. The following figures show the beam pattern size by Woodward-Lawson algorithm with different delta omega. Delta omega is the angular frequency interval. We can find that with delta omega becoming larger, the difference between each patterns are becoming greater. Next, let's look at part 4, the performance analysis of MCBPM. The following figures show that under the condition of different delta omega, the number of information bits carried by each symbol varies with the number of transmit antennas. The system parameters in the simulation are listed in the left table. The actual number of transmitted information bits carried by MCBPM symbol depends on delta omega. In order to show the effect of delta omega, the simulation is applied. By observing the figure, we can see that once delta omega is bigger than thousands, MCBPM excels SM in terms of bit error rate. Whether it is SM or MCBPM, the number of information bits carried by each symbol increases with the number of transmit antennas. Next, we show the effect of delta omega on bit error rate of ABPM. The following figure shows the bit error rate results with the maximized likelihood algorithm under the condition of different M. M is the number of modulation bits. By observing this figure, we can find that when the SNR is low, M has little effect on bit error rate. However, with the increase of M, the number of information bits carried by each transmitted symbol increases. Subsequently, the number of transmitted patterns increases, which leads to the increase of transmit antennas, according to the space sampling theory. Therefore, there is a trade-off between the number of transmit antennas and transmission rate. It is lucky that there are a very large number of transmit antennas in massive MIMO system, which ensures both reliability and validity of transmission. We have known that delta omega has an effect on the Euclidean distance between weighted vectors. The larger the delta omega, the larger the difference between beam patterns. Therefore, the receiver can distinguish different patterns more easily, and the bit error rate performance of the receiver can be improved. To validate the conclusion above, we implement the simulation of bit error rate on different delta omega. The simulation results are shown in the following figure. From this figure, we can see that the bit error rate performance of MCBPM improves efficiently with the increase of delta omega. The simulations above are based on maximized likelihood algorithm, which is known to have the best bit error rate performance. However, the computational complexity is the highest. In order to obtain the trade-off between the bit error rate and the complexity, we implement the simulation about MMSE algorithm, and the results of the simulation are shown in the figure. We can find that, although maximized likelihood is better than MMSE in terms of bit error rate, while as SNR increase, the bit error rate performance of MMSE with different number of receive antennas will gradually improve. If the requirement for bit error rate of the receiver is not high, the MMSE algorithm with a large number of receive antennas is a suitable choice. From the above analysis, we can come to the final part, conclusion. Theoretical analysis and simulation results show that our proposed MCBPM is superior to traditional spatial modulation in terms of bit error rate and transmission rate. Moreover, compared with ABPM, this scheme is more suitable for cellular system. It is worth noting that, due to the limitation of the number of antennas in current base station, MCBPM cannot work efficiently. However, with the prevalence of the fifth-generation network, more and more base stations will deploy massive MIMO. Then, by virtue of a large number of antennae available, we can choose a smaller delta omega to improve the bit error rate and transmission rate of MCBPM, and choose a low complexity algorithm to detect the received signal. Therefore, MCBPM must have some potential applications in base stations equipped with massive MIMO. That's all of my speech, hoping that this speech can be helpful to you. Thanks for your listening. Goodbye.